Welcome to this lesson on refraction. Refraction is the bending of light as it passes from one medium to another. So keywords there. Firstly, the word refraction, it's very similar to reflection, so just take note of the spelling. Refraction is the bending. So bending means changing of direction. Changing direction of light as it passes from one medium to another. What is meant by medium? A medium describes a material, in this case a transparent material for light to travel through, for example air, glass, water, perspex, other types of plastic, indeed empty space. Due to media having different densities, light travels at different speeds in them. So media is the plural of medium, so more than one. They have different densities. So how tightly packed are the atoms and molecules that make up the medium? That determines how much each medium slows down the light that travels through it. And when it changes speed, light changes direction. This causes the light to change paths on passing from one medium to another. Everyday refraction. So here are some examples of refraction that you may have seen in everyday life. The first one shows a pencil, which we know to be straight, and it is half submerged in water and half in air. And it seems to change direction. And that's down to the refraction of light and light traveling at different speeds in water and in air. Here you see an egg half submerged in a bowl of water. Again, we see a different shape. Okay, partly due to refraction, well, fully due to refraction, but also the shape of that bowl, it probably acts as a lens somewhat. And you have seen in your previous lessons on lenses the bending of light, which is refraction, as it goes through a glass lens. And here we see a lovely illustration of the Sydney Opera House through a glass of water. Okay, again, the geometry and the shape of the glass will add to this, and it acts very much like a lens, and the light passing through the water in the glass is changing direction. And there we have some looking glasses, which we've seen different types, concave and convex, which have different effects. They bend the light. Some more. Here we have a raindrop, and there we see it looks like a tree upside down. We've seen with lenses that we can get inverted images when light passes through a lens. Here the medium of water is acting as a lens and it's bending the light. Lovely example of refraction is a rainbow. Okay, rainbow is created by white light coming from the sun, and it passes through many raindrops, and we get a number of things. Firstly, we get refraction, the bending of light, but as we learn in later lessons, white light is made up of a spectrum, a range of different colors, and due to slightly different wavelengths from red to blue, they refract or bend by different amounts, and so refraction of white light can lead to the separation of the colors, and a lovely example there is the rainbow. Here's an optical illusion, okay, where this man's head seems to have separated from his body, but of course it has not. And anything with a lens. Here's a cinema camera which takes a small cinema reel of film, and it can project it to a very large screen using lenses and refraction. So anything with a lens, cameras, projectors, telescopes, microscopes, they all use refraction of light. So let's look at what happens when a ray of light passes from air into a glass block. Okay, so let's start with the incident ray. Okay, and we've had this terminology before when we were looking at mirrors and reflection. So the incident ray is the incoming ray from a ray box or perhaps a laser, and it is hitting this glass block, which is the blue rectangle, at an angle. We draw this line, the normal, at 90 degrees to the surface of the glass block. It's fictional, it doesn't exist in real life, but we use it for measuring. We measure the angle of incidence I here. Okay, so as the light passes from air, so air is outside here, from air into the glass, which is more dense than air, what happens is that the ray of light changes direction, the light slows down, and the direction of the ray moves towards the normal, and we get this angle R, which we call the angle of refraction. And then the reverse happens when the light exits the block of glass. So just the terminology: the incident ray is the light ray before it enters the medium. The refracted ray is the light ray after it enters the medium. The normal line drawn perpendicular to the surface where light enters the medium, and we use it for measuring. The angle of incidence is I, and it's the angle between the incident ray and the normal. And the angle of refraction is the angle between the refracted ray and the normal, that's R. Okay, and here we've drawn a second normal as the light exits the block, and you can see that the exact reverse happens. Okay, we've the angle R within the glass block, which is here, and we've the angle I outside the glass block, which is here. So as it exits, as it goes from the more dense to the less dense material, the ray moves away from the normal. Laws of refraction, and I'm emphasizing the words so that we don't confuse them with reflection, but they are very similar. The first law of refraction says that the incident ray, the refractive ray, and the normal all lie in the same plane. Okay, now this is practically identical to the first law of reflection, except this word here changes to refracted ray. The term plane, recall, means a flat surface in space, and it means that the rays don't suddenly decide to twist and come out of the plane or out of the page if we're drawing a picture on a page. Okay. The second law of refraction is a very important one, and our experiment will be centered around it. It says that the ratio of the sine of the angle of incidence I to the sine of the angle of refraction R is constant. So let's explain that. Firstly, a ratio compares two things. It's comparing something to do with the angle of incidence to that of the angle of refraction, and we show it in the form of a fraction. Okay, then we have the sine of the angle. So this comes from trigonometry, or sine, cosine, tan. Okay, and the sine of the angle of incidence I, so that will be measured in degrees. So the sine of however many degrees, to the sine of the angle of refraction R is constant. Constant means the same or unchanging. So if we put that in more mathematical terms, we get sine I over sine R equals constant. So if you consider the previous slide, and we take the glass block, okay, and we had our normal, and we had an incident ray, with angle I and a refracted ray with angle R. When you divide sine I by sine R, you get a certain value. If you were instead to send the incident ray in at a different angle, let's choose a different color, we have a different I, okay, well then we'd have a different R also. Okay, I'm not sure if that's quite right, but the ratio of sine I and sine R for that same block of glass sitting in the same environment always would give this constant, or would give the same answer. Okay, and indeed that constant means something. Sine I over sine R gives this value n, which is known as the refractive index. Okay, and what is it? It's a measure of the density of the material when compared to a vacuum. Okay, so normally in our lab, I'm going to put an asterisk here and an asterisk here. Okay, normally in our lab, our experiment is carried out in air. Okay, but because the refractive index of air is not that much bigger than a vacuum, we'll leave it go. Alright, technically this definition holds for when light moves from a vacuum into the glass block, and it gives the refractive index for the glass block. Okay, different qualities of glass have different refractive indices. Plastic has a different, or perspex has a different refractive index to glass. Water is different again. Some more on refractive index. The refractive index of a medium is a measure of how quickly light travels in that medium when compared to the speed of light in a vacuum. So vacuum is completely empty space. The greater the refractive index, the denser the material is, and the slower light travels in it. So we can do some comparisons here. So a vacuum, completely empty space, is given refractive index 1. So that's our base to compare everything else to. You can see that air is just ever so slightly above that. Water in the form of ice is 1.31, which of course expands when frozen water does, and so it's less dense, so it has a smaller refractive index as compared to liquid water. The cornea of your eye refracts light some, that's its refractive index. Pyrex, which is the glass that we use in cooking, heat resistant glass, is 1.47, crown glass 1.5, and a diamond, you can see, has a really high refractive index, 2.42, which is why it sparkles and it's refracting the light and it splits it up into its different colors. When a ray travels from a rarer medium into a denser medium, it bends towards the normal. We saw this when the light was entering the glass block on one of the previous slides. So going from air, which is known as a rarer medium, it means less dense, into a denser medium, so like glass or perhaps water. The light ray is seen to bend towards the normal. Okay, and you might have witnessed this yourself if you were standing on the edge of a swimming pool and there was an object on the bottom of the pool and your task was to dive in and retrieve it. Well, oftentimes you might miss the mark as you think it's elsewhere. When a ray travels from a denser medium into a rarer medium, it bends away from the normal. So we mentioned this before also, and this is what happened when the light left the glass block or exited it and passed into the air, which is less dense, and the path of the ray bent away from the normal. Snell's law. So Snell was a top scientist in this area of optics, and this is his law. It says, and we've already seen it, the ratio of the sine of angle of incidence I to the sine of the angle of refraction R is constant. And we've seen this already. Sine I over sine R equals constant, and it is known as Snell's law. And you'll also find Snell's law in your formula and tables books. Okay, the experiment associated with this lesson is the experiment to verify Snell's law, so to show that that ratio is indeed constant. And to do it, you'll be using a light beam and a block of glass, or perhaps a block of perspex. And you'll be showing that sine I over sine R is constant. It's the same. So you repeat it for different values of the angle of incidence. So you point the ray of light at different angles onto your block of glass, and you measure the angles. Okay, here's a diagram that you can use for your experiment report. You'll be using a protractor to measure the angles in question, and a glass block and a ray box. And you'll repeat for different values of I, measure your R, and calculate your ratio. Okay, indeed, if you use your values for sine I and sine R, graph them against each other, you should achieve a straight line. Okay, starting with Snell's law, if we rearrange slightly, we can compare that equation to that of a straight line. Y equals mx plus c. Okay, and as you can see from the graph, sine I has taken the place of y. Okay, and that's why it's placed on the y-axis. Sine R has taken the place of x, and that's why it appears on the x-axis. The slope m is represented by n above. So the slope of this red line should return to us the refractive index of whatever block we're using. And the fact that there's nothing on the end of the equation, plus 0, means that our y-intercept c is 0, and that our graph should go through 0, 0. And that knowledge is useful when drawing your best fit line for the graph. Okay, so on the y-axis, sine I goes there, x-axis, sine R, c is 0, so we know the graph goes through the origin, or 0, 0, and the slope of the line, remember, for slope, you can calculate rise over run. That's your vertical distance, pick a point, your vertical distance over that's your rise, over your run, which is the horizontal distance, will give you the slope. Okay. Key points for Snell's law experiment. If you use larger angles of incidence, they are easier to measure, number one, but if you're out by a degree, the magnitude of your error is not so significant. Okay, so use larger angles, so you're going to use like 20, 30, 40, 50, bigger, and don't be using 10, 15. Use a very sharp pencil, so you get nice clear lines, easy to measure, and avoid parallax when reading the protractor. Now, the refractive index of a liquid, there's a different experiment for this, but you never get questions specifically on one or the other. So I always stick to the glass block experiment for the exam. Okay, so how to calculate the refractive index of a liquid if required? Well, it's equal to the real depth, so that you can see here, this actual depth, so this long distance, the real depth of the water, and you compare it to the apparent depth. So the apparent depth means what you perceive the depth to be, what you think, okay, or what it seems to be. And if you do real depth over apparent depth, you'll get the refractive index of the water there in that situation. Now, your tasks for the rest of the class are as follows. I want you to watch the video of the Snell's law experiment. I want you to begin the experiment report, so you should have a printed version of the template. Fill in what you can. We'll complete this on Tuesday. Fill in the title, date, the experiment diagram, the procedure, etc. And then I want you to answer the exam question given on Snell's law experiment, and I will provide a worked answer for that also. Thank you.